Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows from Aizar Parampur. I am the TA of this course Reagents in Organic Synthesis, instructed by Professor Subhash Chandra Pan from IIT Guwahati. So in this class I usually discuss about the important reagent used in organic synthesis. So and some questions based on that which I have taken from some important books and also from previous year NET and GATE. So from those solving those questions, it may help you to attend the upcoming examinations of your institute or as well as some competitive exams. So let's start. So in the last classes I started discussing from the oxidation reaction. After that we moved to reducing reagents. So if you want to know about the different type of oxidizing reagents, you can go and check those classes. So in the last class I started with this lithium and sodium metal based reducing reagents, which is mainly used in Barch reduction, Today we will discuss about the second one, that is hydrogen donor based reagent or hydride transfer based reagent. Okay, so let's start. So this was one of the exam questions I gave in the last week as an homework, so that you guys try to attempt this. I hope some of you have already tried, but for others I am trying to get the answer of this one. So the major product form in the following reaction. They have asked for the major product form in the following reaction. So from the reagents you can see this is a Barch reduction. From the reagents you can see this is a Barch reduction. In case of pyridine, as pyridine is an electron due to this nitrogen is trivalent. Okay, this nitrogen has already 3 bonds in it. So this nitrogen will not show any plus R effect in this ring. This ring is without the involvement of this nitrogen lone pair. The ring is already aromatic. So there is no involvement of this nitrogen lone pair. Because of that, this nitrogen will not show any plus R effect. This nitrogen will not show any plus R effect. Instead of that, it may show, because of its electronegativity, it shows some minus I effect. Therefore, we are considering this as a electron withdrawing group. Considering this is as a electron withdrawing group. So what happened in case of electron withdrawing group in case of this Barch reduction? I have already explained about the shortcut. So what you can do? So if you consider this is electron withdrawing group, then what will happen? Then you have to keep the electron withdrawing group and draw 2 double bond beside this. So it will be formed. Now in the next, this is the after one. Okay, this is after first step. Now in the second step they have added H plus or H3O plus. H3O plus. So because of adding of H3O plus, this double bond can be protonated and form this. So this will form. After that, due to addition of water at this position, this bond breaks. And form this through minus H plus. From this OH. After that, this OH comes here and breaks this carbon nitrogen bond and form a ketone after the reaction. To form a NH2 and a ketone here. Similarly, the same thing will repeat at this position also. The same thing will repeat at this position also. The same three step will repeat at this position also. These three same step will be repeated at this in this case also. And after that we will get a diketone. We'll get a diketone. Okay. Now see, at the third they have again added this KOH methanol. Whenever you see this KOH methanol and a diketone system is there, so what you will try for? Obviously aldol condensation. Aldol condensation. So if we take a proton from here and if we combine, we'll attack to this place and through elimination of water it will form okay. So it will what will be the answer? Option B. Option B. Understood? So this was the homework. Let's go to the next. So these are some other examples of Barch reduction. It doesn't come to the exam much, but for idea that what will happen if we add sodium or lithium and liquid ammonia into these substrates. So I have shown these examples. So if you take this type of thio compound and add Barge reduction reagent, what will happen? This will be eliminated and hydride will be entered into the alkyl group. After that, if you take this type of thiamide, what will form? This thio group will be reduced and will get this amine from the system. Again, if we add this sodium amide into this tosyl amide, this part will be removed and hydride will be incorporated in the system. Okay, so these are some special examples of Barge reduction. So if we add this Barge reduction reagent into this type of special substrates, what will form? If you got an idea. Okay, so let's go to today's topic. So today's topic is hydride donor based reducing reagent. So there is most reduction of carbonyl compounds are done with this type of reagent that transfer a hydride from boron or aluminium. So here I have shown some important hydride donor reagent. First one is LiLH4, then air aluminium, LiL tertiary butyl, NaBH4, NaBH3CN, boron, AlH3, diacetyl boron, and lastly divalage. So today I will discuss some of them, the mostly used ones which we mainly use in our laboratory in a broad purpose and also in industry also. So I have taken from here, I will explain today some uses of LiLH4, NaBH4, divalage, and finally boron. So we'll discuss these 4 reducing reagents today and we'll solve some questions based on that. So these are the mostly employed reducing reagents, and in our examinations also we have seen that questions comes from these reagents in a greater amount. So next is LiLH4. So lithium aluminum hydride is a powerful reducing agent and reduces most of the commonly encountered organic functional group. Aldehyde, ketone, esters, carboxylic acid, lactones can all be reduced smoothly to corresponding alcohol under mild condition. Carboxylic amide are converted into amine or aldehyde in presence of LiLH4. So this is the in general mechanism. Where I have shown this is the LiH4 and this is the lithium salt. This H minus will be transferred to this carbonyl group, form this type of complex, and again another molecule of carbonyl group will react with another molecule of hydride and form this type of tetramer, and after through addition of water, the workup will get this alcohol in as our product. So LiLH4 can be used for reduction of all these functional groups. If we go one by one, If we add LiH4 in aldehyde, what we will get? We will get a primary alcohol. If you want to know about detail in mechanism, you can go and check books like Claydon and all. And if you want to know from mechanism of the specific reaction which I am talking about, you can ask me, then I will add in the next class. I am not going into the all mechanism for all the questions. I have just shown the general mechanism because I think this mechanism is pretty easy and you can solve by yourself. So if you add ketone in LiH4, you will get a secondary alcohol. If you add ester, you will again get a primary alcohol. Acid also give a primary alcohol. Amide will give a primary amine. Similarly, this one also. If you add LiH4 in oxime, that will also give a primary amine. If you add aromatic nitrite nitro group, it will form a hydrogen type of complex. If you add LiH4 in alkyl bromide, it will simply substitute the bromide from the system. In tosyl also it will just substitute the tosyl group. In case of epoxide, it will open the epoxide. So we are attacking at the less hindered side. So which one is the less hindered side in this epoxide? Obviously this part. So this H minus will attack to this carbon and open the epoxide to form this alcohol. Okay. Let's go to the next some questions based on this LiH4 reduction. So they have given this compound with the NBOC and the CH2 group. LiH4 obviously will not affect any NBOC group, but it will reduce this aldehyde, so this part will be same, just this CHO will be CH2H. I am not drawing the rest part. This part will be all same, just our aldehyde will be reduced to alcohol. Okay. Next is this LiH4 reduction. So this amine is there, so amine is in least oxidation state, so it will not be reduced further. So what will happen? Just our acid will be oxidized, reduced to primary alcohol. Next is this one. Here one amide group is there. There is no such other functional group. So this amide group will be reduced to primary amine, and from this as our product. Okay. Now, if we add LiLH4 in alpha beta unsaturated aldehyde, what will happen? So, alpha beta unsaturated aldehyde are in conjugation with the corresponding aldehyde, which reduces the electron density in the ring. Because of that, we reduces the electron density to this double bond. Because of that, this double bond becomes electron deficient and highly electrophilic. Because of that, this H minus will, instead of this aldehyde, this H minus will attack to this place, and it will reduce this double bond as well as the aldehyde. Will reduce the double bond as well as the aldehyde. But if you perform the reaction at low temperature or with any other reducing agent like dival H NaBH4, in that case this double bond remain unreacted, and we specifically get this carbonyl reduction. Okay, so if you in a reaction, if there is an alpha beta unsaturated group and you are adding LiLH4, both the double bond and the carbonyl will be reduced. Whereas if you perform the reaction at low temperature or with any other reagent like NaBH4 or dival H, in that case only our carbonyl group will be reduced. Next is dival H reduction. So dival H reduce the esters and ketone into alcohol. Dival on reduction of NPTEL gives the amine, and epoxide are cleaved to alcohol. At low temperature, esters and lactones are reduced directly to aldehyde. Nitriles and carboxylamide gives amine, which are readily converted to aldehyde by hydrolysis. So I have shown one of the example of dival H where this ester is directly get reduced to alcohol. Without cleaving the ring. So what is happening? This H minus is attacking at this place and it's opening up to form this alcohol. So in case of dival H reduction, from ester we directly get an alcohol. From ester we directly get an alcohol. Here you can, if in case of ester, if we add dival H, we are getting this CO2 group get reduced and we get aldehyde from the system. The next question, if you add dival H in nitrile, what will happen? CN will be reduced. The CN will be reduced and nitrile will give a primary amine. This part will be same, just it will be a CH2 NH2. Okay. If you add the same dival H into an alkyne, it will undergo a hydrometallation, and in the result through workup we will get a cis alkene. So where this two hydrogen group are adding at the same plane of this double bond. Okay. So if we add a dival H into an alkyne, we will get a cis alkene. We will get a cis alkene. So instead of H3O plus, if you add iodine into it, what will happen? This Al group will be substituted by iodine, and we will get this iodinized product in our system. Okay. Next is NaBH4 reduction. So sodium borohydride is a very selective reducing reagent and reduce aldehyde and ketone to alcohol. Sodium borohydride is a comparatively weak reducing agent, and because boron hydrogen has more covalent character than lithium hydrogen, it does not react or slow react in case of ester and cyclic ester. NaBH4 is a chemoselective reagent for carbonyl compound in presence of esters and amide functional. NaBH4 is insoluble in ether but soluble in alcohol and water, so it is used in hydroxylic solvent like alcohol or isopropanol, etc. So let's go to the reaction. So this NaBH4 will just similar to the LiLH4, it will just reduce the carbonyl groups, but the thing is the reducing property of sodium borohydride are substantially modified in presence of metals, or particularly in presence of cerium chloride. So what happens if we add NaBH4 in this alpha beta unsaturated compound, what will happen? It will just reduce this double bond. As if LiLH4 is there, then both of you will be reduced, but as NaBH4 is less selective, so in this case we will majorly get this carbonyl compound reduced product, but not in the selectivity is not that high. But if we add cerium chloride, what will happen? The selectivity enhances and we get 99% of this product. Similarly, if we add NaBH4 cerium chloride in this compound containing an aldehyde as well as an alpha beta unsaturated aldehyde, what will happen in this case? Can you guess? Due to chelation of this cerium chloride with this CHO group, as CHO group is more electrophilic, this NaBH4 will react with the less electrophilic group and we will get this as our product. We will get this as our product. Similarly, in this case, there is a ketone and an aldehyde center. So which one is more electrophilic? Obviously the aldehyde one. So aldehyde one will chelate to the cerium chloride. Because of this chelation, the NaBH4 will react with this second reactive group, that is ketone, and will give alcohol from the system. So if we want to draw a overview from this reaction, that whenever you add sodium chloride along with the NaBH4, the second reactive group will react in this under this reagent system and give us our product. Okay, so whichever is the most reacting group, that will be NPTEL. Whichever is the second reactive group, that will react and give us our product. This is a shortcut. Okay, because the most reacting group is already reacting with the sodium chloride and get chelated, and because of that it get blocked. So the second reacting group comes close to the NaBH4 and give us our product. Next is boron reduction. So BH3 is a neutral reducing agent which can select for carboxylic acid reduction in presence of the more electrophilic carbonyl groups. So BH3 can reduce the acid group selectively in presence of other functional groups like aldehyde and ketone. So strong anionic reducing agents such as lithium aluminum hydride can reduce carboxylic acid also, but however these reactions are not selective. Even LiLH4 can reduce the other functional group also, so this is not selective for any acid. Secondly, the less nucleophilic anionic reducing reagent such as sodium and lithium borohydride are no longer reactive towards carboxylic group. So this BH3 has come up with a very selective nature which can't be achieved by other reducing reagent. The use of more forcing conditions such as combining NaBH4 with various additives can allow the oxidation of aldehyde, but it enhances the cost of the reaction, high temperature, and most of the case we are unable to get the product. But by using BH3 under room temperature is very easily we can reduce. By using BH3 under room temperature, we can easily reduce acid to alcohol. Okay. So what will happen in this case? So as there is no such acid group, but there is a CN group is there, the CN group will be reduced and give us this primary amine. The rest part will be same, so I am not drawing it. The rest part will be same. Okay. Next is this one. There is an acid group, so acid group will be reduced to give this primary alcohol. From this as our product. Okay. Let's go to the next question. So before that, so till now I have discussed about LiLH4, NaBH4, boron, and divalent. So if we want to know, draw an overview of these four reagents, I have tried to compile them in a one chart. So if you take an iminium ion, it will give an amine. If you take an acyl chloride by LiLH4, you will get an alcohol. From aldehyde ketone, you will get an alcohol. Ester, you will get an alcohol. And amide also, from you are getting an amine, and carboxylic acid will give an alcohol. Similarly, if you add NaBH4 in iminium, it will give an amine. But NaBH4 will not react with acyl chloride, but it will react with aldehyde and ester to give alcohol, but it will not react with amide and carboxylic acid. Again, if you take boron, it will react with aldehyde and ketone to give alcohol, and amide to give amine, and also with carboxylic acid to give alcohol. It will not react with ester and iminium ion. And in case of divalent, it will not react with iminium ion or acyl chloride, but it will react with aldehyde or ketone to give alcohol. Again with ester to give aldehyde, specifically like one step reduction, just one step reduction. From aldehyde, from amide it will give aldehyde, and again from carboxylic salt it will give alcohol. So there is difference. If we add LiLH4 in amide, you will get a, if you add LiLH4 in amide, if you add LiLH4 you will get a primary amine. But if you add dival H, you will get a aldehyde. Okay, so you can, from the chart you can get a short overview of all the reagents. Next class I will try to discuss the other ones. Mostly whatever questions you get in your upcoming NET or GATE, in those examinations they usually include the questions from this reagent. These reagents are also being used, but not in large number. And the reactivity, if you know the reactivity of the NaBH4, you can also kind of predict the reactivity of others, the NaBHTCN and all. Okay, so let's go to the previous year questions. So they have asked, they have given this product and added LiLH4 to room at low temperature. What will happen in this case? So LiLH4 with alpha beta unsaturated compound, what will happen? It will attack to this beta position, it will attack to this beta carbon. Now this methyl is already above the plane, so LiLH4 will come from the below the plane. So LiLH4 will come from the below the plane. So as methyl is already above the plane, the hydride will come from the below the plane. This goes here. On addition of Ac2O, sorry, LiLH4 will just reduce this carbonyl group. As it is happening at the low temperature, I have already in the previous examples I have told, if you perform the reaction at room temperature, the double bond as well as the carbonyl will be reduced. But as the reaction is happening at the low temperature, only the carbonyl group will be reduced and give us this alcohol. Now if you add Ac2O, you will get OAC. Now as Me2CuLi is added, so you can consider this as a ester. So it will attack to this position and it comes up here, and OAC will be removed from the system. Now as methyl is already above the plane, it will come from the below the plane. So this is after reagent step 1, step 2, is after step 3. So methyl is already there, so the new methyl will come from the below the plane. Double bond will shift here. So methyl is coming at this base, double bond will shift here, and OH will be removed from the system. We will get this as our product. Option C. Okay. Let's go to the next question. Identify the appropriate reagent for A and B for following reaction. So you have to identify the appropriate reagent for A and B. Now, how the product of A will be formed and how the product of B will be formed. First we have to get that, then we can choose the reagents. So from here you can see a cyclization is getting performed. In A, this carbonyl is present at this part and there is no such carbonyl. So that means in case of A, this ester will be reduced to alcohol and this alcohol will attack to this acid to form this lactam ring. In case of lactone ring. In case of B, see there is a carbonyl group but there is no such carbonyl group. That means this acid group will be reduced here and attack to this ester group and form this lactone ring. Now, so that means we have to, in case of A, we have to specifically reduce this ester group. In case of A, we have to specifically reduce this ester group, or in case of B, we have to specifically reduce this acid group. So you have to choose the reagent. If you add LiLH4, what will happen? Both of them will be get reduced. So LiLH4 is cut because if you add LiLH4, both of them will be reduced and give alcohol. So LiLH4 is cut. So whichever having LiLH4 in their option, that is cut. So this A and B is cut because LiLH4 will reduce both of them. Now next is, we know to reduce acid specifically, in presence of other group, we use boron. We use usually boron. So for B we use boron. So B as a boron, there is a boron. So the correct option will be option C. And LiBH4 is less reactive than LiLH4, so that will selectively reduce our ester. And whereas the boron will selectively reduce our acid and we will get A and B. Okay. I hope it's clear. Let's go to the next question. So this is based on the theory, the concept we discussed in the last class. I missed this question, so today I have added this one. So this is based on Barch reduction. So if you perform the Barch reduction for, this is a electron donating group. This is a electron donating group. Electron donating group. So if we go by our shortcut, the strategy I have. So we'll just draw the double bond at this, like this way, where the OMe is there. Now in presence of H plus, this ether will break and it will be hydrolyzed to give OH. That undergoes tautomerism. And to get a conjugated structure, there will be a double bond migration. There will be a migration of double bond. get D as our product. Okay, I hope it's just simple. In the following reaction sequence, the structure of the product formed is. What will be the product formed in the following reaction sequence? What will be the product formed in the following reaction sequence? So if you add dival H at -78 temperature, what will form? If you see the ring, there are two 5-member ring where this 2 hydrogen is below the plane. So the ring to the 2 ring is above the plane. These 2 ring bonds are in above the plane. So if you just draw it like this way, so these 2 hydrogens are below the plane. You can imagine it in 3D, right? So the ring is like that. Now if you add a dival H, what will happen? It will reduce the ketone to alcohol. It will reduce the ketone to alcohol. Now the thing is, as the ring is like that, as the 2 hydrogen is already below the plane, and if you want to attack and the ring is above the plane, this ring is also in above the plane. So the attack from this above plane is sterically crowded, but the attack from the below the plane is feasible because of presence of this small hydrogen group. So after dival H reduction, we will specifically get a compound where hydride attack from the below the plane. So the alcohol will form above the plane. Rest will be same. The next, this is after step 1. Next, they have added chloroacetic acid, alpha chloroacetic acid. So what will happen if we add alpha chloroacetic acid? If we add this alpha chloroacetic acid, what will happen? This will attack to this acid group and form a ester. So they have added this alpha fluoroacetic acid, diethyl azocarboxylate and PPH3. Diethyl azocarboxylate means so this leads to the reaction So this oxygen will coordinate with pH3. So the plane will be reversed. When the acid group attack, this will be removed from the system and it will form below the plane. Okay. After that, what will happen? If you add LiLH4, this ester will be get reduced and it will be this bond will break. It will be an alcohol. So the which will be our product? Option B. So option B will be our product. As in LiLH4, this alpha beta unsaturated double bond will be intact. Just this OH group, this it will attack to this position and it will open up like this way. So this alpha beta unsaturated double this alpha beta not alpha beta, this double bond will be intact and we will get B as our product. Okay. Let's go to the next question. So the major product form in the following reaction sequence. So they have added 4-methoxybenzyaldehyde H plus and in the next step they have added dival H. So this 4-methoxybenzyaldehyde acts as a good protecting group for dialcohol. So if we add this after first step, it will just coordinate with both the alcohol. This going through simple aldehyde acetal, it will form a simple acetal. Okay. After that, all these things will be intact. Now if you add LiLH4, a dival H, what will happen? If you add dival H, now in place of dival H, it will give a H minus and this H minus will add up to this position. Now which bond will break? So in case of dival H, if it goes here, the less in that bond breaks, and after our reaction we will get, so this if this breaks, so PMB is attached to this internal oxygen, so option B will be our sorry, not option. So option A will be our correct product because this attacking here. So this or PMB will be attached to this oxygen group only. So option A will be our correct product. Next is this. What will be the most suitable combination from A to C for getting this product? In case of A, what is happening? Only the alpha beta unsaturated double bond get reduced. In case of B, this carbonyl get reduced. Whereas in case of C, this external double bond get reduced. This external double bond get reduced. So for A to reduce the alpha beta unsaturated double bond, what we will use? For alpha beta unsaturated double bond specifically, we usually use Bart's reduction. So the correct option will be between A and B. These two are cut. The correct option will be option between A and B. Now for B, to selectively reduce the alpha beta unsaturated carbonyl compound, we usually use NaBH4 series. In both of the case they use NaBH4. The last reagent we will choose the product. So in the last reagent this external double bond gets reduced. So the first one is the Wilkinson reagent and second one is the simple hydropalladation. So for this one we will use this Wilkinson reagent. So the correct option will be option A. For the use of Wilkinson, this is a homogeneous reagent for hydrogenation. In the next class we will discuss about the hydrogenation. There I will discuss about homogeneous and heterogeneous hydrogenation. Then we will solve some question from that also. Next is this one. So what will be the mature product M and N in the given reaction sequence? So they have added NaH base, CO2 and benzene. So in both the alpha hydrogens are equivalent. So if you just add this is after step A. We will get this alpha ketoester. After that, if you add bromine and ether, this hydrogen is highly acidic. So it gets substituted by a bromine. This is after step B. Now next they have added a strong base, alpha bromo ketone. When added a strong base, what is the reaction it undergoes? It undergoes a Reformatsky reaction. And it will form first it will form this cyclized now as in medium there is OMe minus is present, then this OMe minus will adapt to this side. It will open up from here as this negative charge is stabilized by this carbonyl compound. So it will open up from this plane. So we will get this 5-member ring while there is ethyl group here. And there is a Ca2NO group. After that, they have added divalage into it. They have added divalage. So from the aim, you can get an answer that the correct option is option A. Correct option is option A. Still, they have added divalage, so both the ester group will be reduced, and we will get alcohol from that. So the correct option will be option A. Okay. Let's go to the next question. So this we have done again and again. So what will be the suitable reagent for to reduce the alpha beta unsaturated ketone selectively? So obviously the reagent will be NaBH4 and sodium chloride. Next is this one. What will be the major product formed in the following reaction sequences? So as they have added acid, so one of the ester group will be hydrolyzed. So as this is bulkier ester than this methyl ester, so this will be hydrolyzed in the faster rate to form, and it will give acid. After that, they have added BH3, one equivalent. We know when BH3 is added in one equivalent, it is selective to acid, so it will selectively reduce our acid. And what will be the product? Product will be option D, because the acid group will be selectively reduced in presence of ester when BH3 is added. Okay. Next is what will be the major product formed in the following reaction. So they have taken this substrate and this called contain acid and as well as a ester, and they have added B2HC, that means the borane. So in presence of borane, which will get reduced? I just give 2 seconds. Think which will get reduced. I have already told. So in presence of B2HC, this acid group will be reduced selectively and will get this ester. Will get the ester. After that, this OH will add up to this ester group and remove the OMe from the system. And 6-member ring will form. the correct option will be option B. So the correct option will be option B. Okay. So this is one of the questions. So what will be the major product form in the following reaction? So they have given LDA. So LDA is a base. LDA is a base. So in presence of LDA, it will take a proton from here. So in presence, it will take a proton from here. After that, if you add bromide, alkyl bromide, it will attack to this center and remove the bromide from the system. Now as this auxiliary group contains isopropyl group above the plane, so obviously this group will come from the below. This group appears from the below the plane, so your product will be this one. Now they have added LiLH4. LiLH4 will reduce this amide to alcohol. So the correct option will be option A. Okay. I just keep understood, right? What is happening here? Just it is taking one proton from this alpha position. After that, it is attacking to this electrophile. As this auxiliary group already have an isopropyl group above the plane, so obviously the upcoming group will come from the below the plane, and this benzyl group will come from the below the plane. And when we add LiLH4, 3 equivalent. So the first equivalent, if I go step by step, I will just show. So if they have given LiLH4 3 equivalent, in the first equivalent of LiLH4 will form a aldehyde. The second equivalent of LiLH4 will reduce it to form a alcohol. Okay, so the correct option will be option A. The first equivalent will form this. Second, the first equivalent of LiLH4 will open up this one. First equivalent. Second equivalent will break this amide bond to form this aldehyde. And the third equivalent, will be used to reduce this aldehyde to alcohol. Okay. This is one of the questions we have solved earlier also. If you had aldehyde, it will take a proton from here, ACCl. If selenium chloride, it will enter a selenium at this position. Now if you add this H2O2, it will be oxidized, and after elimination it will give this as our product. This type of question I have discussed earlier also, so I am not going into the mechanism. So from there, so here the main question is from where the proton will be abstracted for first, from at this position or at this position. So obviously this one, because this position is, this hydrogen is more acidic. This hydrogen is more acidic. More acidic. So when we add a base, it will take a proton from at this position. Okay. This is another question. If you add butyl lithium to this position, there is a proton. This proton will be abstracted. So there will be negative charge will be generated here. A negative charge will generate here and it will attack to this beta position and form this as our product. So this A, both the A are cut. So B, this as our product. So X will be this. Again, if we add xylene, through addition of xylene, if there is a proton here, this comes, this take this proton, this goes here, and this is a Chugaev type of reaction. So this gets removed from the system and form this high ester kind of compound. After that, if we add this Hg chloride and cadmium carbonate in H2O, what happens? This ketal get deprotected and we get our carbonyl back. So what will be the product? The product will be this one. This product will be this one. So the correct option is option C. Correct option is option C. I hope you know about the aldehyde protection, deprotection. If you don't know, I will discuss about all these topics in the upcoming classes. I am not discussing here because today's class is mainly based on reducing agent and all the lithium containing compound. So I will discuss this in the next class. So there are two questions. For now, I am just giving this as a homework. You just try this. What will be the product in both the cases? Both are quite similar. The difference, there is a OMe group and there is a phenyl group. So what will be the product in both the cases? As you see, there is a stereochemistry of the carbonyl group. So after this addition of this hydrogen atom, hydride, there will be this attack will be stereoselective. This is not just a reduction. This reduction is stereoselective. So we have to get an idea that how the way hydride will approach our substrate. For that, we have to follow a model called Felkingham model that we will discuss in the next class. If you know about the model, based on that model, we can get an idea that because all these compounds are 3D, you have to imagine those compounds in 3D. So, how the molecule will approach to our substrate to get the product, that can be explained from Felkingham model. In the next class, I will try to discuss about that. After we discuss about Felkingham model, we can solve this question. And if you guys already know about the Felkingham model, you can try by yourself. And next class where I will discuss about this one, you can match the answer if it's correct or not. So I hope you have enjoyed today's class, and it may help you to solve your doubts and your assignments, whichever is given by the NPTEL. I hope I have tried to include some questions which may relate to those, and you can solve those questions also. So thank you everyone. Have a nice day and happy Independence Day belated. Okay, so thank you everyone. Have a nice day.